to. Have people been reading the handwritten notes and the typewritten notes? Like, raise your hand if you've looked at the handwritten notes. And raise your hand if you've read the typewritten notes. So are the typewritten notes an improvement on the handwritten notes? Yeah? Very much so? All right. Because, so previous classes have really, they've, I don't know if I've said before, you know, they've said those handwritten notes are not as useful as they should be. So some people complain about my handwriting. I think the typewriting is better. The one thing that's missing from the typewritten notes still are the figures. So there are no figures, but maybe that will be for next year. It just, like adding the figures, that's a lot of work. So any major problems with the typewritten notes? Any grammatical errors that I make repeatedly? Yes?
No problems, but if you want to add the figures, you can just use like Microsoft Word, and there's like the newest version has like the little draw functions.
All right. So Microsoft Word is really horrible for equations. This is so it's all LaTeX. So we're not going to Microsoft Word. That would be a.
There are equation shortcuts for Word though.
You're killing me. You're killing me. I use Word when I write with biologists, but when it's just me, it's LaTeX. I mean, so really the way that, and also I wouldn't do a drawing. What I would do is actually program the equation for the figure. Like a lot of these figures, like it's really an equation, right? We're looking at the transient. So there's R. So R is a statistical programming language. There's R integration with LaTeX that I can actually put the code for the figure right in there. So that will be the upgrade for next year. Although not all the bugs are worked out of that, but I think it works well enough that that's what I'm going to do. I mean, the other thing I could do is just save figures as PDF or something else and then insert them in. So it's not, that's a much easier way for me than Microsoft Word. Sorry. So any other questions or comments? All right. Are the stories okay? I guess I say the same stories in class. So you got to hear about my car in graduate school. All right, so where we were is we are thinking about, we're going to sort of take an abstract view of our linear system. This should be the last lecture in linear systems. There might be one more lecture on feedback if we don't get to feedback today, and then we'll be done with linear systems. So we have our system response function, so I guess we usually draw systems from left to right, but the math goes from right to left. So we have x of t is the integral to dt prime, h of t minus t prime, beta of t prime, and in Laplace space, x of s is equal to h tilde of s beta of s, where we're imagining that either the system is off at time 0 and we start at time 0 so we don't worry about the boundary term, or we start at -infinity where everything is 0. So we're going to simplify and not worry about the boundary term at time equals 0. And the example that we'll carry through is the cascade that h of s is equal to, not the sum, the product over j, kj over s plus alpha j for a cascade of excitable molecules, where kj is the rate of activation of the molecule j from molecule j minus 1, and alpha j is the deactivation rate, and this goes from 1 to the number of steps in our cascade. So we defined the gain, and all of this will be for the response function. So the gain is defined as 0 to infinity dt x of t divided by 0 to infinity dt beta of t. And we saw that this was the limit as s goes to 0 of x tilde of s, beta tilde of s, and then x tilde is equal to h of s, beta of s. Those cancel. And when we're in the linear regime, we should have a response function that's well defined when s equals 0, as opposed to just s goes to 0. So this should be h tilde of s evaluated at s equals 0. The next quantity that we were going to look at was the mean time of response. So 0 to infinity dt t x of t. So this is the mean time of the output, and then we subtract off the mean time of the input. So that's the mean time of response. And the same way that the gain, when we're in Laplace space, is easy to calculate, in Laplace space, the mean time is easy to calculate. So here's how we do it. So so this is the sort of thing where if you start with the answer, it's easy to work back to the starting point. So the answer is that for some time domain function, so say that f of t is a time domain function, and t bar is just defined as 0 to t dt f of t times t normalized by the area of the function. So here f is sort of working like a weighting function, and t is a variable that we're taking the average of. We'll show that t bar is equal to minus dds log of f tilde of s evaluated at s equals 0. Or really limit as s goes to 0, just in case f tilde is not defined at s equals 0. Right, there's a question.
Yeah, t bar is the mean time of what?
Of response, or of the function. So it's sort of like we have this function f of t. So here is f of t, and we want to choose this function, this time t bar, so that this area is equal to this area. So it's the mean. The first moment. So the first moment. So these are moment generating. So we'll see that Laplace transforms are moment generating functions. The 0th moment maybe is the area. So that is f at 0. And then every time we take a derivative, we get the next moment. So here, this is the first moment of the response, is the mean. All right. So we'll prove this. So we have minus dds of the log of f tilde of s is equal to minus dds. So the first thing is that we'll use the chain rule. So the derivative of the log of f is equal to 1 over f times the derivative of f. So this is 1 over f minus dds f tilde of s. So that's just the chain rule. So this is 1 over the Laplace transform, and then minus dds And now we'll just put in the definition of the Laplace transform. 0 to infinity dt e to the minus st f of t. And the only dependence on s is in the exponent. So we'll move the derivative inside the integral. And then when it works on the exponent, minus dds of e to the minus st pulls down a power of t. So this is equal to 0 to infinity dt e to the minus st t f of t divided by 0 to infinity dt e to the minus st f of t. So that is the Laplace transform of f. And then in the limit the s goes to 0, we get what we wanted. So that's the proof. And the only reason why it's the limit instead of s equals 0 is for things like the step function, where as t goes to infinity, this diverges, and so you don't really get a result. All right, I saw somebody's hand up. Nope. All right. So now for the time of the response, so using this, so what that is equal. So now this is minus dds log x tilde of s minus dds log beta tilde of s, and so that's minus dds log of excuse me?
You're saying log, but you're writing log.
Well, that's how I pronounce that.
It's always in base E, right?
Yes, so it's always in base E. If we don't specify the base, it's always base E,
Okay.
because
I just assume when someone says log, that it's
yeah, no, base 10 is an accident that we have 10 digits. So if we were Sumerian, though, we'd be using base 12 and base 5 and base 60, which we do for telling time still, but there you go. So then those cancel, and we get just minus dds log of h of s, and then this we should be safe evaluating at s equals 0. So now this is much easier to calculate than going into the time domain and then doing a bunch of integrals in the time domain to calculate the mean. So for example, for the series, for the series response, so let's see. So I'm going to erase this. So the gain was h leave s equals 0, and then for our series circuit example, that was the product over each step of the gain for that step. So here the mean time is minus dds of the log of h of s at s equals 0. So this is equal to minus dds for our example, the log of the product over j of kj over s plus alpha j. I'm going to erase more. So when we take the log with respect to s of these activation rate constants, those are all 0 because they don't involve s. So this is the sum over j of dds, the log of s plus alpha j, evaluated at s equals 0. So that's the sum over j 1 over s plus alpha j at s equals 0. So sum over j 1 over alpha j. So alpha j is the relaxation rate for each step in the cascade. 1 over alpha j, the inverse of a rate, is a time, so that's the time for each step in the cascade to relax. And then we add them all up, and that's the activation, that's the response time for the whole cascade.
Adding them up seems counterintuitive. Intuitively, I would think that would be the mean of the whole stuff, the mean of each.
Well, but so the thing is, like, so we're thinking about putting together a bunch of response elements like this, okay? And so each of them will have some response time, I don't know, like tau or delta t, that we sort of have to wait till the next one gets triggered.
It's also happening consecutively, not all at once.
Yeah, so like first, so this is a cascade where each step activates the next step. So first this step has to get activated, then this step has to respond, then this step has to respond. So the response time is the sum of all the individual response times. If they were all the same and we had n of them, it would be n times the response time for a single element. Yeah?
I apologize if you mentioned this, but in that first transition from the DDS natural log of, it's not the summation with multiplication, to the summation one, where does the k term go?
Oh, where it goes is that DDS of k is equal to 0, because this is a parameter that's the activation rate. It's like a biochemical rate constant. So alpha j is also a biochemical rate constant, but here we have the log of s plus alpha j, and when we take the derivative with respect to s, we get 1 over that.
Gotcha.
So that's like, it's really simple. So the other thing that we see is that the production rate doesn't affect the response time at all. That the production rate affects the gain. So that if we step up the production rate to go from this step to this step, we don't make the response any faster, we make the amplitude bigger. So that's also what we saw before with the single, with I guess the response to an oscillating input, that the gain involves the production rate, but the phase shift only involves the time rate constant.
And the alpha j is which one again?
So the alpha j, so here's our model, is that, so the model for the cascade is that xj dot of t is equal to kj xj minus 1 of t minus alpha j xj of t. So each step in the cascade gets activated by the previous step. So it'd be like a signal transduction cascade where one protein phosphorylates the next protein. And then alpha j is the dephosphorylation rate. So, so kj, it's actually a bimolecular rate constant because we have the inactive form of the protein that is being phosphorylated by the active form of the previous step. But we're making the approximation that we're in the weak response limit where even though each step is getting activated, most of the protein stays in the inactive form. So all of this is in the weak response limit that lets us use linear response. But linear response really, whenever there's a linear response, whenever we're approximating a real physical system by linear response, really what that means is that it's sort of the low input level. So this is low input. If we're, so we'll get to sort of high, so the high input case, or positive feedback, the signal is so strong that all of the protein is in the active state, and then we'll need a sort of different set of a different type of model to represent that type of system.
Will we just incorporate the Hill equation?
Yes, we'll get a Hill equation. So that actually, so the Hill equation is also cooperativity. So that's cooperativity plus saturation.
What would just be saturation?
So, I mean, the Hill equation is a general form, but usually people talk about a Hill equation with a Hill exponent. So I'd say like Michaelis-Menten. So when people think about Michaelis-Menten kinetics, you get saturation because all the enzyme is being swamped by substrate, so it can't run any faster. So that you get saturation, but without what people call ultrasensitivity, that it looks like a titration curve. So like saturation, the Hill equation is a little more general because it has saturation plus cooperativity. So here's what we're saying.
Just set cooperativity to 0 then?
Yeah. So, Michaelis-Menten is a special case of Hill equation.
Oh, okay.
So here's sort of what I'm saying in pictures. So say that our input is going to be just a constant input. So at time 0, we turn on the system. And here's our output. So x is going to be, in the linear regime, it's going to be k over alpha times beta 0. So as beta 0 increases, our output increases. So here, this is sort of just one level of one step in the cascade. So at some point, we'll be saturating the system that we don't have any more protein to activate. So instead of getting linear response, it will be sublinear. So eventually we'll get saturation. So this is the linear regime where we have small input, then input gets bigger, bigger, and bigger, and then eventually we saturate, we don't get any more input. And in some systems, actually we can have a downturn, like you've overdone it and you've killed the system. Like, you've redlined your engine, so you're stepping on the gas, and then your engine finally brakes if it gets too high. In addition to saturation, we can have a different effect called cooperativity that you probably had in molecules and cells. Oxygen binding to hemoglobin is an example, where as the system gets further along in the cascade, it's easier to go to the next step. And then what you get is a response that looks like this instead. So this is cooperativity, which will be, so these two nonlinear effects, saturation and cooperativity, we'll cover in the next section of the course. Saturation just comes because you have a finite system, or at least for us it will be because we have a finite system. Cooperativity comes from non-independence between the signaling molecules, that if they have interactions with each other, they can affect each other's behavior. Okay. So we've looked at, so now we've looked at these properties. So now if we just think about our response function h of t, because we're focusing on response. And so here's an example of what one might look like. So the area, that is our gain. So we'll call that G. And then the mean value, that's t bar, so that's h of s at s equals 0. So that's minus dds of the log at s equals 0. And something else that we will be interested in is the width, so the duration. Duration or width, and we'll define this as the variance, the average of the square minus the square of the average, so just like variance in prob-stat. So this is equal to 0 to infinity dt f of t, t minus t bar squared, divided by 0 to infinity dt f of t. So exactly how you would define a variance for a random variable. And this is equal to minus DDS squared log of h of s at s equals 0. So I think the proving this is one of the homeworks, I think. And if it's not, it should be. But I'm pretty sure it's one of the homeworks. So we won't go through the proof. It's just the same as this, except you're taking one more derivative. And it comes out. And just the way that the proof for the mean, the easy way is to go from this derivative to the formula for the variant. For the mean, the way to go was you start with the derivative of the log of the response function, and then you see that's equal to the mean. Here you start with the derivative, the second derivative of the log of the response function, and show that's equal to the variance. So in random variables, or in prob stat or electrical engineering, these are often called characteristic functions. So response function in the Laplace domain is a moment-generating function or a characteristic function that you can use to generate the moments of the time response. So it's easy to calculate the duration, or really the mean square duration of the cascade. So, so T average squared minus T bar squared is minus DDS squared log of the product over J, Kj over S plus alpha J. And we've already done the first derivative. So doing the first derivative gets us to here. So it's equal to minus DDS of the sum over J, 1 over S plus alpha J, evaluated at S equals 0. So now we just have to go term by term and take one more derivative. So this is equal to the sum over J, 1 over S plus alpha J squared at S equals 0. So it's sum over J, 1 over alpha J squared. And the units work out because this is supposed to be a square width, and we have a time squared. So the units are right. So in the case that each step in the cascade is the same, this would go to n over alpha j squared. This goes, or n over alpha squared. This goes to n over alpha. So the variance and the duration, the time delay of the response and the width of the response both scale like the number of elements in the cascade. So this is the variance of the time response. If we wanted the width, we would take the square root. So the width would be square root of n over alpha. So as we add more elements to the cascade, we push out when the mean time of response is, and we also get a longer response. So a cascade gives us a longer response and also a stronger response, but at the expense of having to make a lot more different types of proteins to hook in one to the next. All right. So this is a serial pathway. In the notes, we also work out the result for a convergent or branching pathway. So here, we have the same input going into two different subsystems, and then we get an output. So here we'll see that the gain is equal to the sum of the gains for each branch, and the overall mean time of response is equal to the gain weighted mean time of response. So these aren't formulas to memorize. This is more saying when you put things in the Laplace space, these results are very easy to calculate. The result for the variance is a little more complicated to calculate, so that's not in the notes. But it's just, you just have to take a derivative and you get the answer. So also in the notes, so there's an example of response to drugs. So is there much to say here? So there's a worked example that so these sorts of relationships give guidance for thinking about real world problems. So one real world problem is pharmacogenetics. So what that means is that we have genetic variants that affect how we metabolize drugs. One of the major types of genetic variants are variants of a protein called cytochrome P450. There are lots of different proteins in this family. So this isn't one protein, it's a whole family of proteins. They use the heme group to do redox reactions. And the idea is that, so like you have your liver is filled with cytochrome P450s. So CYP is the abbreviation. And one thing it does is that often when you take a drug, it's not in its active form. So you take a prodrug, and then the prodrug gets transported into your liver, and drug comes out. So that's one way that cytochrome P450s affect drug metabolism. The other way is that when you have a drug in your system, there are different ways of getting rid of it. One way is to excrete it, so it goes out through your urine. But another way is that you metabolize it into inactive metabolites, so things that don't have drug-like activity. So it goes into your drug, it goes into your liver, and your liver metabolizes it. So if we think about the gain, so now you get a drug. So we have, so the gain, which in terms of drugs people usually call area under the curve. So you take a drug and they measure the level of the drug in your blood over some amount of time. So what is the area under the curve? So that's going to be the product of K, say, prodrug to drug, and then K, drug to waste, divided by alpha prodrug to drug, alpha drug to waste. And the mean time of response is, well, actually I wrote product, but here, like not really product. And then, we'd also have terms that have to do with drug action. And then the mean time of activity would be something like alpha prodrug to drug plus 1 over alpha drug to waste. So what happens with drug response is that we didn't really evolve in the presence of drugs. So there are a lot of genetic variants that just naturally occur in cytochromes that, that end up causing large changes in drug metabolism rates, because before you're taking these drugs, there's no selection for fast response or slow response to a drug. And the level of variation in drug metabolism response is greater than the level of variation in response to normal metabolites. So what that means is from person to person, we can have large variations in the degradation rates and also large variations in these activation rates. So one example that's actually pretty common is grapefruit juice. So there are many drugs that you're not supposed to drink grapefruit juice while you're taking. And the reason is that grapefruit juice has components that are very strong inhibitors of the cytochromes with half-lives of like 12 hours or 24 hours. So if you have a glass of grapefruit juice, the cytochromes can be inactive for half a day to a day. So what that means is that if that cytochrome is important for the transition from prodrug to drug, you'll get very much less gain from the drug. The drug will be, you take something in prodrug form, it will be excreted before it becomes active. However, sort of on the other side, it could also interfere with the drug to waste step. So imagine that you're taking a drug in active form, and now the drug level, the dosage has been calibrated for normal liver activity, but now the liver enzyme isn't working. So alpha will become much smaller. The rate of transition from drug to waste will be smaller. So the mean time of response will be much, much larger, and also the gain will be larger. So quantitative details in the notes. But if you're wondering about why grapefruit juice has so many drug interactions, that's why. And actually, there's some drugs that you take with another molecule that has a very similar form to try to take advantage of lengthening out the time of activity to make sure that the drug doesn't get metabolized quickly so that it has more of an effect. All right. So now questions on gain and mean time of response. Yes?
So how did we get that, the AUC equation, the gain for the AUC again? Is it just, how did we get that?
So we're just defining it, the gain as the area under the curve, and the area under the curve of the response function. So if we have a bigger input, we'll have a bigger output. The response function connects the input to the output, and if we're in the linear regime, then it's all explained by the response function. So does that answer the question, or is that just not really so helpful?
I'm just confused on why you're multiplying the two activation.
Because think of this as, so for this drug example, so think of it,
so like if you were to do a diagram, like the diagram you drew over here.
So here's an ODE. So here's this example as an ODE model. All right. So prodrug at time t, that's under our control. All right. So but then, so this is like say, and then we have d dot of t. So the rate of change of the drug is equal to a rate constant k from prodrug to drug, P of t minus alpha d of t. So here we would just have one step. And the reason is we weren't really thinking about metabolism of the prodrug. So here the transfer function, so here we'd have d of s is equal to k prodrug to drug over s plus alpha times the input prodrug that we control. And then we'd have genetic variation in this rate constant k prodrug to drug and genetic variation in the degradation rate alpha. And and typically the genetic variation causes these rates to be smaller, say. So if prodrug to drug is smaller, then we decrease the gain and we don't really do much to the response time, it's still the same. If we reduce the degradation rate either because of genetics or because of an environmental factor like grapefruit juice, then we increase both the gain and the time of response, and somebody's a super responder. Yes?
We never accounted for the drug being metabolized back into the prodrug, did we?
Excuse me?
Was the metabolism of the drug back to prodrug?
So usually that's an irreversible reaction.
Oh, okay.
That, often we have enzymes that I mean, things should be reversible, but I think these things are thermodynamically favored to go in one direction, or also stoichiometrically favored to go in one direction. All right. So now we'll take a look at a paper, and then we'll go back to it. Just wait while the projector warms up. Main PC. Why isn't it on? Oh, it's up on the screen, but it's not up here.
You probably have to double screen.
Let's see. All right. So what we'll be working through is the theory to understand pathway diagrams like this. So if we ignore the side pathways, let me see if I can make this bigger. Let's see, Shift plus. Ha, there we go. All right, so this is what caffeine does to you. Here we go. All right, So we'll look at the bottom pathway. So they're really the same pathway, except the bottom one is just the pathway on caffeine. So you'll see a cascade from an adenosine receptor to, so that's the receptor, and then it activates adenylyl cyclase, which generates cyclic AMP, which is a signaling molecule. So this is one of these intermediate pathway outputs in a cascade. Cyclic AMP activates protein kinase A, which in turn phosphorylates a protein called DARP32. I think 32 must be probably the size of the protein, like if you did an isolation where it would end up in sedimentation, I think. And that phosphorylates a specific tyrosine, tyrosine 34. And then DARP32 inhibits protein phosphatase 1. So protein phosphatase 1 is one of these proteins that's responsible for the off step, for taking phosphate off of a molecule. And then protein phosphatase 1 in turn inhibits phosphorylated target proteins that are activated by protein kinase A. All right. So we understand this part of the pathway because it is just so it's a series of steps, and it has one branch in it, but it has some negative steps. We've just really been dealing with positive steps. But in pathway pictures, 2 negatives, so 2 inhibits is equal to a positive. So if A inhibits B and B inhibits C, that's sort of the same, at least in a linear system, as A activating B and B activating C. So you think about, like, the signs, you just take the product of the signs, it ends up being positive. So that's the main pathway, and we'd know how to calculate the gain and the time of response for each step, and we'd be good. And we've also learned that longer pathways have maybe more gain and more response. So possibly cyclic AMP is acting as an amplifier. We don't know. Another reason that there's signaling intermediates is that a lot of signaling proteins have evolved from common ancestors, and the shared cofactors are retained. And so one of the puzzles is, why isn't there more crosstalk? There are other kinases other than protein kinase A that are activated by cyclic AMP. So when your receptor gets hit by adenosine, so adenosine is a normal signaling molecule in the brain, and generates cyclic AMP, why doesn't cyclic AMP activate other kinases? So this is one of the puzzles. So in fact, often it does sort of excite other pathways to lower levels. There's another reason that people have explored is scaffolding, that often these proteins aren't just floating around in cytoplasm, they're all anchored together in a scaffold. So the cyclic AMP doesn't have that much time to diffuse away before it hits the next molecule. And then we also, sort of embarrassing, I guess. I don't know, it's not really embarrassing to go to the bathroom. Everybody goes to the bathroom. All right, so as long as you're going to the bathroom in the bathroom, which is something that my kids are still learning. So, okay, so there are also other enzymes in cells that degrade molecules like that, just to sort of keep the crosstalk from happening. So we could work out what's going on with the main pathway, but then there's this other branch. So this branch of the pathway generates feedback, and now I think there's different, so it generates feedback that here is shown as negative feedback on protein kinase A. I don't know why that's up there in that one. And I think this, so the story in this picture is that caffeine generates negative feedback on protein kinase A. And caffeine is also an inhibitor at the top of the pathway. And so if you think about sort of in the sense of two inhibitions causing activation, more caffeine causes this feedback loop to run more and more. And as a result, there's sort of positive feedback that the modulation to the signaling pathway caused by caffeine encourages more of the same modulation. So caffeine is a negative in this picture, so it's inhibiting this receptor. And also caffeine is strengthening this connection, and so there's sort of synergy that gives positive feedback, so that when you drink a cup of coffee, there's the effect of the coffee on the top of the pathway, but also there's the effect of this feedback loop. And the paper that is motivating the example is a study where in mouse knockouts, so a very common way of studying human genes and signaling pathways is to use a related species like mouse. They have mutants that either have the main pathway running alone, or the main pathway plus in the wild type the regular pathway, and then they look to see the difference in caffeine response in the two types of mouse. So what we're going to do is work through the math of positive and negative feedback in signaling pathways in the linear regime, and then we'll be done with linear systems, and we'll move on to nonlinear systems. And we'll come back for a review of the actual paper with the mouse data. So I think at this point, this research is like maybe 10 years old. 10 years old? Maybe not, maybe about that much, 10 years old. Okay. All right, so now we will turn that off and move the screen back up. All right. So we'll start with no feedback. So we have our signal beta of t, so this is caffeine, say. Well, I guess what we left out of that picture was why caffeine? So it turns out that one of the so caffeine is mimicking a naturally occurring neuroregulator called adenosine. So that's the same adenosine as an adenine as in one of the nucleotides. Just like cyclic AMP is a cyclic form of adenosine monophosphate, one of the nucleotides. So nucleotides, in addition to being part of nucleic acids, like RNA and DNA, are also signaling molecules. So this is a signaling molecule that's floating around in your brain and around neurons. And adenosine hits, I think it's called the A2A receptor for adenosine receptor type 2A. And then this inhibits activity. So more adenosine, it's a neuromodulator, it decreases neural activity. Caffeine is an inhibitor of A2A, so it binds, but it doesn't activate it. And as a result, neural activity is uninhibited, and let's see, your neurons are more excitable. So that is how caffeine works at a molecular level. And what is going on in this paper is that there's a feedback loop that inhibits part of the pathway. And since caffeine is an inhibitor and the feedback loop is an inhibition, and if instead of thinking about 0 and 1, you think about 0 as being more of a baseline, and then you can be above baseline or below baseline, then the two negatives end up being a positive if you think about the pathway output being positive neural activity. So that is that's caffeine and adenosine. And actually in the paper, sort of a bigger picture is that there's similar receptors that respond to dopamine, which is a stimulatory pathway, and drugs like L-DOPA are an attempt to make neurons more stimulated in people with disorders that neural activity is too modulated. All right, let's place that. All right.
Regarding drugs that stimulate neural activity, is there some difference between drugs that are not able to pass the blood-brain barrier but able to activate your central nervous system instead, somewhat? Does that exist?
So I think anything that crosses the blood-brain barrier is also going to be in your blood serum. So the challenge, I think, is more in drug development is more to get drugs that pass the blood-brain barrier. But there are definitely, there are a lot of muscle relaxants that work on skeletal muscle, say, or So I'm not sure how much they pass the blood-brain barrier. I'm also not entirely sure of their mechanism of action, what pathways they're going into. But for example, just magnesium. Magnesium is a common muscle relaxant given to women in preterm labor to stop labor by stopping the muscle contractions.
I thought magnesium was good for smooth muscle contractions in terms of your GI tract, though.
It's more like I think you need it, but taking magnesium weakens muscle contractions. All right. So here's the model that we'll start with. So we're putting in a cascade with a couple steps so that we can see how everything adds up. So here goes. So in the time domain, our model is x dot of t. It's going to be k x beta beta of t minus alpha x x of t. And y dot of t is k yx x of t minus alpha y y of t. So the standard model that we've been using. And just to keep track of what everything is, we'll have subscripts for the activation rates that go from the upstream to downstream. So that as you read the symbols, you see there's a beta there, and a beta there, and an x there, then an x there. And then the degradation rates will have the subscript for what's being degraded. And as usual, we will simplify our thinking to imagine that at time 0, everything is off, so we don't have to worry about boundary terms. And we get the standard solutions. So x Laplace transform is kx beta over s plus alpha x beta. And then y is equal to k yx over s plus alpha y x. And then, so finally, we substitute x response in there. So we get k yx, kx beta over s plus alpha y, s plus alpha x. beta. So this piece we'll call the response function, and we'll put a 0 because it's the feedback-free response. So that's just the response for a cascade. So H0 of S is equal to just the main part of the cascade. All right. So now what we're going to do is we're going to add some feedback. So we're going to say that as a model for the cascade, this output activates another signaling protein Z that then feeds back to X. So we're going to add a feedback loop. So with feedback, we are going to add a plus K X Z Z of T. So that's X feeding, that's Z feeding back to X. And dynamics for X. So K ZY Y of T minus alpha Z Z of T. So remember off to the side that in the feedback-free case, we have this response function. Okay, X beta over S plus alpha Y, S plus alpha X. And what we want to calculate is the response function with feedback. So we won't have a subscript here because this is really what we want. Okay. So now, those results. So, so now X of S is going to be Kx beta over S plus alpha X and then beta plus the part that depends on Z in the solution. So we have a Kxz over S plus alpha X Z of S. But we don't know what Z is yet because we haven't gotten that far. So the ODE for Y is the same. Z is equal to KZY over S plus alpha Z Y. And then we can substitute for Y in terms of Z. So we get KZY, KYX over S plus alpha Z, S plus alpha Y, X. And then this solution for Z goes here. So we get Kx beta over S plus alpha X times beta. And then plus this new part that is the feedback. Yes?
Sorry. For your, why would your Y dot of T not change considering you have something going from Y to now Z?
So it changes, but it only changes because the input X is stronger now. So the ODE for Y is still a production based on X and degradation of Y. All right? So this ODE doesn't change. The ODE for X changes. So the solution for X that we'll put in here will be different. So it changes through its linear dependence on X.
I guess the same way that X changes because of the added from Z, I don't think, so is that Y to Z term, is that just Z of T maybe is not, or why does that not, make another decay function from Y to Z? that make sense? Right.
So here is Y decaying, and here is Z decaying.
Right.
All right.
So is that alpha Y then in this new feedback or sort of takes into account both the degradation to Z or whatever?
So Y is like, it's a kinase, it's phosphorylating Z, all right? So it doesn't go away when it does that, it's a catalyst. All right, so now we have this term to put in. So we have K xz, kzy, kyx divided by s plus alpha x, s plus alpha y, s plus alpha z, x of s. And for shorthand, we are going to call this term. So if you look at the picture, what this term is it's the response function for one trip through this loop. So you can sort of picture it as the response function to get from x to y, then from y to z, and from z back to x. So if we just had a linear pathway that, like, we sort of unwound this and we got back to x, this would be the response function for a pathway, a cascade with 3 steps. So we'll call it HL. So L stands for loop. So lowercase l's are bad to use in notation because they look just like ones, but uppercase l's are good. So it's the loop response function. So that's the response function for the signal going through the feedback loop once. So then, all right, so x of s is equal to kx beta over s plus alpha x, beta of s, plus the response function through the loop times x. And then we'll just bring this term to this side and then divide by 1 minus HL. So we get 1 over 1 minus HL kx beta over s plus alpha x beta. And then our solution for y is that y is equal to kyx over s plus alpha y times x. So we have this 1 over 1 minus HL in front. And then we get kyx, kx beta over s plus alpha y, s plus alpha x, and then beta. And then this part we'll recognize as the feedback free response function h0 of s. So in the end, what we get is something very simple that we get 1 over 1 minus HL times H0. So this is the pathway without feedback. This is the pathway with feedback.
What are we setting S to in these circumstances?
So here, I mean, here we're still in Laplace space, so we haven't set S to anything yet. But we're about to set S to values and take some derivatives.
What values and why?
So the first, well, we want to calculate the gain, say. So how does this positive feedback affect the gain? So that's a good question. So to figure out how it affects the gain, so we don't need these ODEs anymore, because here's this picture, it's doing it for us, that we used to have a pathway that went from input to a signal, and now we've added a feedback loop, a positive feedback loop, and what does it do to the amount of drug action? So if you take a drug and you integrate about how long your pathway is active, what is the gain. So here, so we could call G0 is the gain of the feedback-free system.
You were just talking about how long the path is active, what gain can do to...
Well, for these sort of systems, how long it's active is similar to the average time of response. So what's the average time of response? So here, well, here the gain is the integrated area. So if we divide the integrated area by the duration of response, we'll get something that's like amplitude. And actually, the notes discuss that a little bit, but it ends up not adding that much because it still scales like the response time. Like you saw, the variance scales like 1 over the response time squared. There's a difference of a square root in the number of pathway steps, but in terms of like the overall picture, it didn't seem like it.
Okay.
Yeah. So here we have, you know, k yx kx beta over alpha y alpha x. So here, so remember, this is just, so the gain 0 is h tilde 0 of 0. So the gain with feedback is h tilde of s at s equals 0. So it's equal to h0 of 0 divided by 1 minus h loop of 0. And then we could write this as the gain without feedback divided by 1 minus the feedback gain through the loop. And the feedback gain through the loop, I mean, remember the loop is just a 3-step cascade, so we can just write it down as this is.
We need an associate for gain loop. That's a 0.
So the gain is equal to the response function evaluated at s equals 0.
Yeah, so I mean, G subscript L kind of ambiguous. It seems like
No, so we're defining GL as h tilde L of s at s equals 0. So it's just this product, k, what was it, zy, k, yx, kxz, divided by alpha z, alpha y, alpha x. So these are positive. So gain loop is positive. 1 minus gain loop, as long as the gain through the loop is less than 1, then we increase the gain for the pathway. So you can just sort of see mathematically how that happens. We get into trouble when the gain through the loop gets so big that it gets close to 1. Then the gain diverges because the loop never turns off. It takes a long time to turn off. If the gain loop is exactly equal to 1, we get an infinity. And then if the gain of the loop is bigger than 1, it looks like we get a negative answer, which wouldn't make sense. But really what that's telling us is that we've left the linear regime, that our linear approximation is no longer good. We have saturation. And you know, one possible result is that actually the signaling pathway stays active, that the strength of the feedback is strong enough that we're locked into the active state. All right, so we're done for today.